Next problem. Says the area of the first parallelogram is 150. Let me write that down. No, actually the second one. The area is 150. The area of FGHJ is 54. If the two parallelograms are similar, find the scale factor and find the value of x. Now the scale factor, we're given two areas. We're doing these backwards. So let's do it like this. Tell me, what can I multiply 54 by to give me 150? Is it 2.7?
2.7778.
So we'll call it, well, it's not really the scale factor, is it? Remember when we discussed yesterday, the scale factor is what I can multiply x by to give me 10. The areas are different, so the scale factor, and to actually find the scale factor between the areas is actually the square of your normal scale factor. So what did you say, 2.1?
7.
And the way he found that was this. 150 divided by 54. Whoops, try again. 150
Same answer.
divided by 54. It's missing a 10 there. There's your scale factor, 2.7 repeating. But now that's the scale factor, my normal scale factor to the second power. So what can I do to find my normal scale factor here? Take the square root. So the scale factor between my sides will be 1.6 repeating. So what that means is I can multiply this by 2.7 repeating to give me that. Take the square root of that. That means I can multiply this by 1.6 repeating to give me 10. But the problem is I got to go from 10 backwards. If to go from x to 10 you multiply by 1.6 repeating, how do you go from 10 back to x? You divide by it. So to figure out what x is, we're going to do 10 divided by my answer. That gives me 6. Now let's check that. Let's do it forwards now. My scale factor from, actually let's do it different, just to show you both ways. Let's work it this way now. I want to know what's my scale factor from 10 back to 6. 10 times what gives me 6? 10 times what? Here's your equation. 10 times what gives me 6? That's 0.6, right? You can check that. 6 divided by, whoops, that's not divided by. 6 divided by 10, that's 0.6. So to go from here back to here, you multiply times 0.6. But now areas are different. If you multiply by 0.6 to go from here to here, well, how do I do my areas? 0.6 to the second power, which I believe is 0.36. So my scale factor from 150 to 54 should be, if I did it right, 0.36. Let's check to see if it is. If I take 150 and I multiply times 0.36, I get 54. So that does check out. So the relationship between scale factors, linear scale factors squared give you area scale factors. And later on we'll talk about volume next chapter. Linear scale factors to the third power gives you volume scale factors. So here's the same thing, but let's do it in the direction because, look, they give you 6 and you're asked to find x. So let's go in this direction. Let's go from the big shape to the smaller shape. Now dealing with scale factors, if you're going from a large shape to a smaller shape, we're scaling it down. Your scale factor should be smaller than 1. Because think of it like this. If you multiply something by 1, it stays the same. If you multiply something by 2, it gets twice as big. By 3, it gets 3 times as big. If you multiply something by half, it shrinks half the size. So therefore, anytime your scale factor is bigger than 1, it grows, smaller than 1, it shrinks. So from 72 to 50, I should have a scale factor smaller than 1. So we're asking ourselves, 72 times what gives me 50? Have you got it yet? That would be divided by 72. And that would be smaller than 1. Say 50 divided by 72. And that gives your area a scale factor of what? 0.0.
So you do 50 divided by 72.
That's it.
0.694444.
And I'm going to leave that on my calculator. 0.694 repeat. Now let's go a step further and talk a little bit of algebra. That means this is 69% of the size of that. That's all it means. Okay, and that's how much you scaled it down. You scaled it down to 69% of your original shape. Now you got to be careful. That's the scale factor between your areas. The scale factor of the areas we know is the square of your normal scale factor. So the normal scale factor to the second power we know is equal to 0.69 for repeating. So how do we find our scale factor? Our normal linear scale factor. Anybody? Take the square root. So your normal scale factor is 0.83 repeat. So to go from here to here, we're going to take 0.83 repeating of that. So again, to scale something down, and our area is 69% of the original. Our side lengths are going to be 83% of the original. So you're going to take that at 0.83 repeating. You're going to multiply it by 6 to scale that 6 down, and you now have 5. So x would be 5. So we've got several questions we could answer here. The scale factor of the blue to green figure, well, we did it backwards, didn't we? I think we did it the easier way. But if you want to do the scale factor of the blue to green, instead of 50 divided by 72, you'd have to do 72 divided by 50. And it might actually have been a nice, neat whole number. 72 divided by 50. Yeah, 1.44. That was a little bit cleaner. So the scale factor the other direction is 1.44. Now, what's the relationship between this and this? They're reciprocals of each other. If one of them was 2/3, the other will be 3/2. And then I believe if you did that again, I think that would make this 1.2. Would be the scale factor from x to 6. If you go backwards, you go from 6 back to x, you would actually divide by 1.2. 6 divided by 1.2 gives you the exact same answer. Next problem. We're given an area and another area. And again, look, notice where your 40 is at. We want to go from 40 to x. So let's go in this direction. We want to know what we can multiply 400 by to give us 64. 400 times something gives me 64. It should be a number definitely smaller than 1. 0.16 sounds good. 400 times something is 64, so we're going to do 64 divided by 400. And like you said, it's 0.16. So that means that your new area is 16% of the old area. You scaled it down 84% of what it was before. That's our normal scale factor squared. So to find the actual linear scale factor, we take the square root of that, which I believe would be 0.4. So what y'all got? Square root of 0.16. So to find what our new side length here, we're going to take 40. We're going to multiply it times 0.4, and we now have 16.
Yeah, 16.
Any questions? And do you see how that changed the area? Changed the area by a good bit. See if we got some more. Now this is, I don't know how much we're going to work with this, it's just an interesting thought. In lesson 7.2, you learned that if all corresponding angles are congruent and the corresponding sides are proportional, then the polygons have to be similar. We'll take regular polygons. All regular pentagons are proportional. They're similar. All regular hexagons are proportional because all the angles are the same. And y'all remember how to find the angles? You take the number of sides, take 2 away from it, multiply it by 180. And then if all the angles are the same, then we'll divide it by however many there are, and that tells us how many there, how big each angle is. Well, if you're dealing with 2 hexagons, all their angles are going to be the same. All their side lengths are identical as well, so obviously they're proportional. All the sides are the same, all the angles are the same. So therefore, if you've got 2 regular polygons, they're going to be similar. I don't know what the information at the left is, but Orlando and Mia are making a scale model of a pentagon. If the area of the base of their model is approximately 50 square inches, about how many times the length of each outer wall of the pentagon is the length of We don't have the information to the left, so I guess we can work that one. Let's try another one. But what we get out there, I will say this. You're dealing with two pentagons, and let's just kind of make up a problem here, because I don't want to completely skip. So you got a pentagon, and you got a duplicate, or a scaled pentagon. It's a little bit bigger, maybe. Duplicate. There we go. We know that if the area of this is 50, the area of the base of the model is about 50, then this other is going to be similar to it. Let's say the side length here, and I'm making this up. Let's say the side length here is 4, and the side length here is 8. It's twice as big. I'm just making this problem up, but let's go with it. How much bigger is the side length of the bigger pentagon? What's our scale factor there? 2. From 4 to 8 would be 2. So would our area be 100 here? No. It would be 200. If you got a scale factor of times 2 linear-wise, then the areas will have a scale factor times 2 squared, or times 4 would make it 200. Okay. Didn't want to just skip that completely. Miyoki is crocheting 2 circles. The area of the, by the way, are all circles similar? You know about that?
Yes.
Yeah, all circles are. All circles are similar. The area of the larger circle is 2.5 times the area of the smaller circle. So you got 2 circles. Their areas. The area of this one, area is 2.5 times greater than the area of the smaller one. Now, does that mean the circumference will be 2.5 times as big? No. No. Circumference is a linear measure. Area is not a linear measure. So let's talk about what would actually be the scale factor there. If you're going to multiply times 2.5 to give me, to go from here to here, how would I go from circumference to circumference, or from radius to radius? What would be your scale factor there? 2.5 to go from the area of the smaller one to the area of the larger one, you multiply by 2.5. So to go from radius to radius, or to go from circumference to circumference, you would not multiply by 2.5. That's the ratio of the areas. That's the scale factor of the areas. How do you find the linear scale factor? Anybody? Oops. 2.5 is the ratio of the areas. That's your normal scale factor squared. So you're going to take the square root of 2.5. So about 1.58. So your normal scale factor, you're going to multiply by 1.58. And that's if you go from radius to radius, diameter to diameter, circumference to circumference. Okay, those are linear measures. Area is not a linear measurement. So here we go. The area of the smaller circle is about 50.2 centimeters. So I've got all that information on here. Let's erase that and start over. The ratio of the areas, which do they give you? They give you one area, don't they? 50.2. Square centimeters. The area of the larger circle is 2.5 times as big. So somebody tell me what that area was. So the area of the bigger one is 125.5. All we did there, guys, was we multiplied times 2.5. It's 2.5 times as big. But if we are given the diameter, let's see, well, we're not given the diameter of each one. It says, if that's the ratio of the scale factors, what's the diameter of the larger circle? Now the area, go ahead. Yeah, area is pi r squared. If the area is 125.5, this goes back to old stuff, equals pi r squared. Let's solve that equation. We want to know what the radius is. What's the first thing you move? Pi. So we're going to take that 125.5. 125.5. We're going to divide it by pi. enter. And then we're going to, how do you get rid of the square?
Square root.
So now we're going to square root it, and that should be the answer. The square root of my answer, about 6.32. And that's the area, the big one, or that's the radius, the big one. Radius is 6.32, the diameter, 12.64. Now let me show you this. There's another way of doing it, but here's the thing. If that's the diameter of the larger one, we should be able to find the diameter of the smaller one, not by dividing by 2.5. Okay, that's the scale factor of your areas. If the scale factor of your areas is 2.5, then the scale factor of your, I think we did it a while ago, scale factor of your side lengths and all that would be, was it 1.58, the square root? 2.5, 1.58. So what you could actually do, now that you've got the diameter of this, if you want the diameter of this one, just take that 12.64, divide it by 1.58, and that should give you the diameter of the small one. Okay, 12.64 divided by that answer up there. So about 7.99, right around 8. And you can check it. If the diameter is 8, that means the radius is 4. That means the area is 16 pi, 4 times pi, 16 pi, which is 50.26. That's pretty close. It was rounded. Okay, moving on. Way too much information. Last thing we're covering, geometric probability. That's all. Geometric probability. A good example of geometric probability, everybody loves the roller ball here, right? You roll the ball up, try to get it into different. Now here's what you got to be careful of with probability. When you're dealing with probability, the chances of things happening must be equal across the board. What I mean is, like, if I say, what's the probability of drawing an ace out of a deck? Then each card that you draw must be equally likely in order to be able to find the probability of drawing an ace. We know there's 4 aces in a deck. We know there's 52 total cards. So the probability of drawing an ace would be 4 out of 52. The probability of rolling a head, of flipping a head on a coin, well, there's 1 head. There's 2 different things on the coin. That'd be 1 out of 2 or 50%. That's the type of probability we're doing today, but we just got to make sure it's geometric probability that all things are equally likely. Because with this game, I would say that there's some skill involved as well. Now, if you just closed your eyes, rolled it, maybe not as much skill involved. We got to make sure that as we're doing these probabilities that everything's equally likely. Length probability. If a line segment contains another segment, such as here, A, B, C, D, and we want to know what the probability of picking a point off of this BC as opposed to picking something off of the entire line. It says that's to find that probability, you would find the length of segment 2 out of the length of the whole line. Okay, really easy. And here's how you would write that. The probability that the probability that you're going to pick some point that's on BC, the probability, that's what that P stands for, the probability that E is on BC would be the length of BC over the length of AD. Same thing with the cards. Here's your problem. Point X is chosen at random somewhere on line JM. And we want to know what's the probability that it's going to be on KL. The probability that if we pick a point, okay, if we close our eyes and we come up here and you point somewhere on this line, the probability that you're going to point somewhere on line KL. Well, how long is KL?
7.
Careful, KL is 7 out of the length of the whole line. Let's talk about, if you've never seen this before, the relationship between fractions, decimals, percents. I can take this fraction, I can reduce it if you want to, or you can just divide it. Let's change this thing to a decimal. 7, this line means divided by. 7 divided by 14 gives you 0.5. That's your decimal form. If I want that in a percent form, which most of the time probability is written in percent form, we take that decimal and move it over twice. That would be a 50% chance. Now, why is there a 50% chance that if you pick a point that it's going to be on KL? Because KL is half of the line. Okay, so obviously that'd be a 50% chance of happening. These are pretty easy. Point X is chosen at random on JM. Now, was that last one? Is that not the same problem? Oh, well. What's the probability that you choose an X value that's on LM? Well, how long is LM? Out of the whole line, yeah. Back when you were doing the whole probability of choosing a red marble, if you got 5 reds and 2 blues, you know, it's the same type problem. So we got 4 out of 14, which when we reduce it gives us about 0.28. Somebody divide that for me. 4 divided by 14.
0.285.
What's your next number?
7.
So we'll call it 0.286, which is about, and I should put about there too, 28.6% chance of that happening. Because again, that LM is a little over a quarter of the line. A quarter of the line, well, if it was 16 long, it would be exactly a quarter, but that's a little bit more than a quarter. And the last one here, what's the probability that X is on KM? KM has a length of 10. The whole line has a length of 14. We don't have to work this problem.
11.
Yep.
KM has 1.
Oh, it's 11?
Yeah.
I did the wrong one. There we go. 11 out of 14. 10 would have been so nice because 10 was going to work together with 14 very nicely. 11 out of 14. That'll work that last one out. Yeah, LM, okay. 11 out of 14, which is about 0.3 decimal places.
0.785.
Which is about 78.5% chance of that happening. Pretty likely. If you choose a point, what's the likelihood that it's going to be a point that is on KM? Pretty likely. Nearly 80% chance of that happening. Let's do this one. It says iced tea at a cafeteria-style restaurant is made in 8-gallon containers. Got to be cautious here. Each tick mark is 1 gallon. 1, 2, 3, 4, 5, 6, 7, 8. We want to know, okay, it says once the level gets below 2 gallons, the flavor becomes weak. What is the probability that when someone tries to pour a glass of tea from the container, it is below 2 gallons? So we want to know the probability that's in this region or this region as compared to the whole region. Well, that'd be there's 2 chances out of a total of 8 chances. There's 8 total regions that this tea could be in. But the probability that it's going to be in this region or this region, that's 2 chances out of the 8, which is, if you want to reduce it, 1 out of 4, 0.25 exactly, or that's a 25% chance that it's going to be below 2 gallons. What is the probability that the amount of tea in the container at any time is between 2 and 3 gallons? The probability that it's going to be in this region. 1 out of 8. Which would that not just be half of what we did over there, which is about 12.5% chance of happening? And that's pretty easy. Let's talk about area probability and then we're finished. Same way with this linear, that what we just did was linear. Okay, we're talking about the probability that's on a line. Well, what's the probability like a dartboard? What's the probability of throwing something at a dartboard, no skill? Okay, we got to factor out skill here, just randomly just throwing it at the dartboard. That it lands in certain places. It all has to do with the area. Okay? If we want to know that, it says if region A contains a region B inside of it, and a point E is chosen randomly somewhere in this region A, and we want to know what's the probability that it's going to be in B, then we would find the area of region B, how big it is, compared to the total area. Pretty easy. So the probability that's going to be in B would be the area of B over the entire area. Here's your problem. Suppose a skydiver must land on a target of 3 concentric circles. And what concentric circles means, they have the same center. You got one circle, you got another one around it, and then you got another one around it. We want to know if the diameter of the center circle is 2 yards. What's the radius? 1, right? And the circles are spaced 1 yard apart. Okay, let's go through and do all these. The distance from here to here is also 1, so what's the radius of that circle?
2.
2. And then the radius of the biggest circle would be 3.
I think it depends on going on 3 yards or
Yeah, I think so. And here's something else too. That's like if you drop him out of the airplane and it's just randomly. There's no skill. Again, there's no skill, because if there's skill involved, then that's going to increase the probability that he's going to land in the middle area. So this is, take out the entire skill part. What is the probability he will land in the red circle? So if we know he's going to land somewhere on this target, let's first find our total area. Area of a circle, r squared. So what's the area of the entire big, huge circle? The radius is 3, so the area is exact. Let's do exact. I'll show you why in just a second. What's the area of the whole circle?
9 pi.
9 pi. That's the area of the big circle. Everybody, that makes sense. We want to know the probability he's going to land in the small circle out of the big circle. Okay, based on the big circle. What's the area of the small circle? It has a radius of 1. Pi times radius squared would be 1 pi, or just pi. And there's a reason I told you to write it down as exact. So therefore, the areas compared to each other. The center area is 1 pi out of the total 9 pi. So if I want to know what's the probability that he's going to land in that middle region, that's 1 pi out of the 9 pi. And the reason I wrote it like this is because pi's cancel each other. The probability he's going to land in the middle region is a 1 in 9 chance, which if you type that in, that's about 0.1 repeating. Actually, it's exactly 0.1 repeating, or 11.1 repeating percent. He has an 11% chance. If he lands on that circle now, I'm not saying he might land out here. That's if we know he's going to land on the circle, because that's the 9 pi. If we know he's going to land on the circle, there is an 11.1% chance that he's going to land in the middle region. Yeah, not a very good chance. Now let's make it a little bit tougher on him. What's the probability he would land on the blue region? How in the world do you find the area of the blue region?
Just the blue region?
Just the blue region. Because, here we go, let's draw it.
Or do you take like the white and the red and add them together and subtract it from this?
Yep. To find the area of this blue region out here. And again, I remind you, the radius was 1, the radius was 2, and the radius was 3. And I want to know what's the probability that he's going to land on this outside region. Now, I still know the whole area. The whole area is 9 pi. To find the chance that he's going to land on this, I need to find the area of this outside ring. Well, the whole thing is 9 pi. Everybody knows that. Well, is the outside ring not that whole area take away these middle 2 areas? Well, what's the middle 2 areas? What's the area of these 2 put together? The radius is 2. Careful. Oh, that's the outside. The area of this inside ring, the radius is 2, so therefore the area was pi radius squared is 4 pi. The area of this middle 2 rings put together is 4 pi. The whole thing is 9 pi, so this outside ring will be 5 pi. So the probability that he's going to land in the blue ring will be 5/9. If you change that to a decimal, that's exactly 0.5 repeating, which is going to be 55.5 repeating percent. Okay, now let's do the white region the easy way. That's the probability that he's going to land in blue.
You could add the percentage for the red and blue.
Last up, we did the probability that he's going to land in red was equal to 11.1 repeating percent. Guys, he's going to land in red, white, or blue, one of the 3. So what we can do is, if the chances of red is 11.1%, the chances of blue is 55.5 repeating. If you add those together, that is 66.6 repeating percent. Well, that only leaves the probability of the white, which would be the rest of the 100%, which I believe would be 33.3 repeating percent. That's the easy way of doing white. Guys, those events are called complementary. If I tell you the probability that you're going to get, I've got a bag of marbles, and I tell you the probability that you're going to reach into that bag and draw out a red marble is 2/3. What's the probability that you're going to reach in and not draw a red?
1/3.
1/3. The complement of that, the other stuff. That's what we did there. We used complements to find the probability of white. That's a whole lot easier than the other method. Okay, a couple more problems, 2 or 3 more problems. Let's do this one. We'll skip the next one. What's the probability? This is a tough one. Use a spinner to find each probability. What's the probability that the pointer is going to land on yellow? Now, that's not 45%. That's 45 degrees. The probability that it's going to land on that, well, we need the area of that compared to the area of the whole thing. Well, that's 45 degrees out of how many degrees? Yeah, that's 45 out of the 360 degrees, which I think is 1/8, which is about 12.5%. Divide 1 by 8, you get 0.125, that's 12.5%. The probability it's going to land on purple. I would say that would be 0% chance to happen. Everybody understand? Can't happen. The probability the pointer is going to land on neither red nor blue. Is that red?
I think the brighter one is red.
This one here? What's that? I think this is orange. I think this is orange. So the probability that it's not going to land on red or blue, well, that would be, again, we're dealing with complements. The probability that it does not land on red or blue would be the probability that it does land on yellow, green, or orange. Now, there's 2 ways of working that. You could deal with the red and blue. Let's do this. Let's do, what's the probability that it's going to land on red or blue? Because there's only 2 of those. What was the red and blue? Mark them out.
105 and 70.
105 and 70, which would be 175. The probability it's going to land on red or blue would be 175 out of the 360 degrees. Well, the probability that it's not, therefore, without even having to add those up, would be the rest of it, which I think is the 185 out of 360. You can work it either way. 175 out of 360. We'll work it together. 175. Push the calculators down. 175 out of 360 gives you a 48.6% chance. Or 48.6% chance. So therefore, the probability that it's not, which is what we're looking for, would be the rest of it. Would be the 185 out of 360, which should be 51.4% chance. So you can do it either way. There's 2 ways of working this thing, guys. You can do it the easy way or you can do it the hard way. Let's talk about the hard way first. Yeah. The hard way is to find the area of the whole thing. Looks like the radius would be 5 for the whole circle. We will know the probability that we randomly choose something that's in the shaded region. Randomly choose something that's either here or over here. So that would be the area of the shaded region out of the entire area. The area of the whole thing, radius is 5, would be 25/5. And then you could go in and find the area of this, find the area that's pointless.
Would that just be half?
Yes. If you took this section, moved over there, because the reason I give you this problem, I want you to understand that what you're doing is you're finding the area of your shaded part compared to the area of the whole part. Half is shaded. So the probability that you're going to choose something in the shaded region without even working it out is 50% chance. Last problem. Now this one, this is a doozy. Find the probability that a point chosen at random lies in a shaded region. First step, let's find the area of the whole region. This is going to kind of bring everything back together that we've done in this chapter. First step, let's find the area of the whole region. This is a hexagon. Let's draw a hexagon down here. This is a hexagon that has a side length of 8. I assume it's a regular hexagon. If it wasn't, we couldn't work it. When we're dealing with the area of polygons.
In hexagon, aren't they triangles?
Yep, I believe that's right. Area is equal to 1/2 AP. The central angle, since it has 6 sides, the central angle would be 60 degrees. And if you wanted to do it like that, it would be 60, 60, and 60. So, but let's take and dissect this thing. This is 8. Your central angle is 60, so that means that this would be 30 degrees. So you actually have a 30, 60, 90 right triangle. If the whole side is 8, that means that this section is 4 and this section is 4 because it's also isosceles. If the shorter side is 4, we need apothem. If the shorter side is 4, the apothem is going to be 4 root 3. Everybody good with that? So therefore, our area of the whole area, I'm going to do area total, would equal 1/2 times the apothem, which is 4 root 3, times the perimeter, which is 8, 8, 8, 8, 8, 6/8, which is 48. So it'd be 96 root 3, I believe. Leave it exact. Leave it exact. Now let's find the area of the small hexagons. It's going to be very similar. We find a central angle. It's the same scenario. Since there's 6 sides, that makes this 60 degrees. If you took and dissected it again, if this whole angle is 60, that makes this 30. That makes this 60, makes this 90. The side lengths now are 3, which makes it 1.5 and 1.5, which makes the apothem 1.5 root 3. So the area, let's do it in red. The area of this small hexagon, area would equal, area would equal 1/2 times the apothem, which is 1.5 root 3, times the perimeter, which the perimeter of this would be 3 times 6 is 18. 1/2 of 18 is 9. 9 times 1.5 is 13.5 root 3. That's the area of the white portion. That makes sense. There's 4 of them though. So let's do 4 times that area. 54 root 3. Okay, let's take into perspective. The area of these 4 things added up is 54 root 3. We've got an issue here. We want to know the area of the shaded region. We want to know the probability it lands in the shaded region. So how do we find the area of the shaded region? The whole thing has an area of 96 root 3. That's all of it. These areas added together are 54 root 3. Take that away. The area of the shaded part would be the whole total area. Take away the 54 root 3, and you're left with 42 root 3 is the area of the shaded region. Nearly done, right? And I told you to leave it exact for a reason. The probability that if we pick a point at random that it's going to be in the shaded region would be the area of the shaded region divided by the total area. See why I told you to leave it? Root 3's cancel. Leaves you with 42 out of 96, which I believe would reduce to 21 out of 48, which would reduce again to 7 out of 16. There's a 7/16 chance, which if we did on a calculator, some of you already got it, a 7 out of 16 chance would be about a 43.75% chance. That's exact. Okay, that's not rounded. There is a 43.75% chance that if you chose a dot at random, that it's going to be in the shaded region. Another way of looking at it, 43.75% of that shape is shaded. Okay, the area of the shaded region divided by the area of the total region gives you 0.4375, which is 43.75%.